in the course of your working with Matlab, you find that Matlab is really limited in terms of how much computations it can do, and it slows down. And that slows down because it just can't do computations fast enough. And that's because Matlab is a scripted language. It goes line by line every time you execute it, while C and C++ are compiled languages. So that way they keep everything ready and you can just quickly get things executed. And so typically when things require heavy computations, Matlab really takes, it could take days what C would take a few hours, okay? So an example, so here is a way in which you can actually not totally stop using Matlab. You can still use Matlab and you take all the heavy parts in your code and put them in C so that you can get the best benefits of Matlab, which is quick prototyping with the heavy computational efficiency of C and C++. And the way this goes is through a file called MEX files, which are files which you can use to communicate between Matlab and C. Okay, and the way this thing works is in Matlab, it's going to look very much like a regular call. Like if you want, there's a function fun, it could be addition, subtraction, integration, whatever you want to call it. A comma B here, I just put random inputs A and B. It doesn't have to be 1, 2, it can be any number of inputs. They are inputs to a C file, and then the output is something which comes out of using those A and B. It could be A inverse times B or whatever you would like. But this file is where most of the work is in writing. That is, you need to write what is known as a gateway function, capital F. Okay, this gateway function is written in C, and it talks to Matlab in a very regular fashion on Matlab end. So this is what a gateway function looks like. It always has the same syntax, and what you write code is going to go here. You need to include mex.h, and then you need to include these 4 parameters. Now, these 4 parameters are basically telling you what the inputs are. So the inputs are the RHS and the number of arguments in the RHS. Okay, so you could have A, B, C, D, E. If those are your inputs, then it will say that there are 4 inputs. That means NRHS is going to be 4. And then the PLHS is basically the left-hand side. And so you could have any number of left-hand sides at x1, x2, x3, so on. So then in that case, if it's this 1 to 3, then NLHS would be 3. So that's pretty much what it needs. MX array are special arrays which are used for the communication. And these stars are actually pointers in C. Okay, so you don't really send values, but you send pointers. Okay, so I'm going to show you a very simple example on how to actually go about doing this. And some point of time, you might have to do this because you see Matlab goes slow. So what I provide you with first is this file, and I called it template.c. Let me just find it on my end. Okay, so this is something which I'll give you, template.c. Let me not play with this. Let me make the first file. Let's call it hello.c. Okay. Okay, and so that's file. We open it, it's the same file. Okay, so if you want to write, say, I want to print the same famous hello world phrase, then instead of saying printf, which is the standard syntax in C, you put MEX printf. And so you hello world, and that's it. Okay, so once you have this, now the thing is, how do you actually go about using this? So this is how you use it. First, let me, let's see. Okay, so I need to be in this folder. That bugs me. So let me get to this folder. The easier way of getting this, well, I could do CD and get to this folder. The easier way of getting into that folder is the following. You just make a file there and then just run it. But I'm just seeing how to, let's see, make a file. Can I make a file here? Probably not. Okay, so I just have to bite the bullet and get this. So let me just go to this path. This is the easiest way to do it on Mac. CD that. And then if you do pwd, present working directory, you are in that MEX class, okay, which is where my file is. Okay, so first things first, before you can run any C files or MEX files, you need to be able to compile them, which means that you need a special compiler which you can access through Matlab. And to do that, you need to say MEX setup is the first step. And then you do this, in this case, MEX is already configured using Xcode with Clang. It's already saying that MEX is configured. If it is not, I mean, if you want to choose something else, like if you want to do Fortran, you just have to say the right syntax. But if you see that it's not configured, then just do max help and it'll tell you what compilers Matlab can use. And then you have to download those compilers and go with that. You don't really need any paid ones. There are free ones which do the job. This one comes with Mac code and it works fine. Okay, so once you have that, then you need to compile this file. So you say MEX hello.c. And then if it's successful, it says MEX completed successfully. Now what I'm going to do is I could call this in this fashion, hello, because that file is called hello.c and it should run fine. So if I run this, it says hello world, which means it ran this file. I'm just going to make a new file and I'm going to call it through this. It'll be helpful later on. So I'll call it hello. And then I can say MEX hello.c. So that's to compile it. And then if you look actually at, let me just see this first. So I'll just save it as test.m. Okay, so if you see this, it created this new file, MEX-Mackay64. Now, if you were using it on a Windows machine, it'll create a DLL. If you use it on Linux, it'll create a different format. I forget the extension. So it just depends on your platform. I can delete this, and now I can compile this, and so you'll see that it'll actually appear here. Because we'll compile this first and then execute hello. Okay, hello world. And then if you open it again, you'll see that it was created. Okay. It'll actually tell you if you're in error. So if you try to use printf, for example, right? And then if you run this, okay, so here it actually didn't compile it. It pretty much, it should have checked the date and compiled it again, but let me clear this. It should give an error. Oh, really? That's interesting. I don't think this, I didn't expect this to work. Let me just change this and see if that works. Interesting. I did not know that you could get printf to work. When I tried this earlier, it didn't work. Okay, so printf works just the same as MEX printf. Okay, so this is how to write a simple hello world, but it's more useful if you can pass in arguments and do some calculations to get them back. So what we'll do is we'll do something in Matlab and try to do the same thing in C. Okay, just to check. So let me generate a random 3x3 matrix, and this is just going to show you how to pass a matrix to Matlab. Okay, and then maybe get it out. So A equals, say, manipulate. So this is just taking in the matrix A and then shooting it out, right? And so what you expect is when you run this file, you get the same A. So let's just try on working on this. So right now, if I just run this, it'll give me some random matrix which are inputted here. So let me make a file called so in MEX. So let's take the template, copy it. Let's take this file name. Okay, and then open it. Okay, so now we have some idea about what the inputs and outputs are going to be, right? The inputs are, it's going to be a single input, it's going to be a single output. Now for, let us do it this way, actually. Let me just print it out first to explain some of the intricacies of Matlab. So, sorry, MEX files. So I'm going to just input that and print that within Matlab, or sorry, the C file. Okay, so here we go. Let's first get the number of input arguments. So this is the syntax which is specific to how MEX files are written. And the best way I can show you is just to just write it down, right? And then you can just try to go from there. So you need to get the sizes of these arrays which are passed. So I'm going to use m rows 1, n columns 1. I need a pointer for A. Okay, and then I need two I and j in order to keep track of the I and j matrices of I and j indices of the matrix A. Okay, now what I'm going to do is I'm going to get the dimensions of A. So I do m rows A1, which is this one, is basically mx get m, and this is a syntax which is specific to MEX files. This basically what it does is it takes the RHS, the 0th argument. So remember that in Matlab, you start numbering from 1, but in C, you number from 0. So this is taking the first argument, input argument, and then getting the rows of it and assigning it to m rows. Okay. Similarly, you can get the columns. And for that, the syntax is mx get n. Okay. And if you want to check anytime, you can do since printf works the same, you can do %d m rows. This should be n columns. Okay, and if we compile this, it should print in this case 3 and 3. Okay, let's just run this. So we go here and say MEX on this. I did a typing error. This m rows 1, columns 1. So it printed 3, and that's what I expected it to print. Okay, let's keep working on this. Now I need to assign this A matrix A to the pointer to the input argument. So I set the pointer to A to mx get PR. Okay, this is the get pointer, PRHS 0. So all this while we are just getting the rows, the columns, and then of course the actual matrix. Okay, now we've got the matrix. Now let's try to print it, right? So the standard way of printing a matrix once it's in C is through this syntax, and this is pretty much taken from other sources. I less than m rows 1, I plus plus, and then for j equals 0, j less than n columns 1, j plus plus, and then a I j equals. So by the way, I need to assign a has not been defined, so I can. Okay, the problem with this way is that I actually need to assign a big enough space. So I can put 3, but if it's going to be bigger than 3, then this is going to give me an error, right? I need to pre-assign the size of a matrix. I can, with pointers, I don't really need to assign the size. This is one of the limitations, and there are ways to get past this. You don't need to assign, you don't need to put 3, but you can make a dynamic allocation, which I'm going to skip here. It's just going to make it more complex. So aij equals the pointer a plus I times n calls 1 plus j. Okay, and once we assigned that to a, we can then print a. So this is the assignment. Now we're going to print, and for that I need to do it this way. So print f percent, let's say 14 decimal places with a tab, and then a I j f new line, so that each line comes on a new. Each line comes on a new line, and I think that's about it. Okay, now let's just run this. So this is going to print the A, and then the same A is going to go here, and we'll see that output immediately. Run this. Okay. Okay, that's a simple error to fix. Okay, so you can see that we have 0.149, 0.257, that's something wrong. 0.149 is right. 0.2542, you can see 0.2575, 0.92, 0.84. This 0.84 looks like it's been moved. So it looks like A over here is the transpose of this A. Okay. Is this, so the question, is this C or C++? This is C because I'm using the .c file, but you can do this with CPP too. You can name that as CPP, and C and C++ are cross-compatible. In fact, you can actually, what I've done in the past is I have some C files and I have some CPP files, and you can just link them. That'll work too. So it's really, that's fine. Okay, so here is the problem. That is, this matrix is a transpose of that one. Okay, so this is one of the things which you want to remember. Matlab is based on Fortran. Okay, initial work. So the person who developed it wanted to write a simplified version to work with Fortran. So he developed Matlab to work with. So it's sort of a wrapper on Fortran so that it will make life easy in Fortran. That was the whole intention. So it has inherited all the things on Fortran. In Fortran, when you have a multi-dimensional array, it is stored column-wise. Okay. In C, the matrix is stored row-wise. And so when I try to access this and try to access the values row-wise, I get this problem where it gives a transpose. So the way to fix this is, well, you could fix it this way. Whatever you get here, you can take it and transpose it. Or if you want to fix it in the code, what you do is, instead of taking it as I comma j, you take it as j comma I. And this will also take care of it. So if you run this now, then you see it's 0.25, 0.6. The first column looks exactly the same second. So this is how you need to take a matrix and sort of manipulate it. Okay. So what I'll do is, instead of trying to get it to print the output, which is again get A, let me just develop another example where I take another input B, okay, where B will be 3, 1, and then I show you how to do A times B and then print that output X in a file. So let's comment that out. Let's take a new 3 by 3 matrix, and then let's call our new one to be matrix vec mult, and inputs will be A and B. And for now, I'm just not going to develop the output. Let me just develop the code for this, and then I will develop the code which prints the output. It's just easier to develop code in systematic, step-by-step fashion. So I'll need to MEX it. And I can actually build off this code. So let me make a copy of that code. And then make this the file name. Okay, and open it. Okay, so my first goal is to actually get the A and B matrices into this file and print them out. That's my first goal. I already did that with A. Now I need to work with the other one, which is B. So let's do that. Okay, so since I had a second vector in input being input, I still have to treat it as a matrix. So I do m rows 2, n calls 2, right? And then I need, let's see, so I need to do the same thing for B. So it'll be m rows 2, n calls 2. In this case, it's going to be the first argument. Well, it's really the second argument, but by notations, it's 1 because the way C works. And then I need this to point to B. Okay. Now this is a one-dimensional array, right? It's not a multi-dimensional array. So I just said B, and then I need to create a pointer for that. So I create a pointer to B. Okay, and I think that's all I need. Okay, so with that, let me just try to print this. So I can comment this out. For I equals 0, I less than m rows 2, I plus plus. What I needed to do is I needed to print on the new line, so in B I. Okay, I think this will work. Let's try it out. So test, I need to initialize B. Okay, and see if this works. Okay, just to compare B and B. Okay, there's a problem here. This should be right here. Okay, let's run this again. Okay. We got something different. Okay, we need to fix this. Why is that different? Oh, I see the problem. This should be, I just did a mistake here. This should be pointer A0, and this should be B, and there should be 1 here. Okay, I think it should work fine now. Okay, there we have the same output. So that shows that A and B are both input. Now let's just try to see if we can do A times B, right? Matrix A times matrix B. So the way this is done, and this is really C code on how this is done, we basically initialize something called a sum, which keeps track of the sum. We initialize an output variable, let's call it X. And then the way this will go is, let's comment this out. We don't want it to print. So we need to sum each row. So we do it the following way: for I equals 0, I less than m rows 1, I plus plus. Then I initialize sum to 0.0. And for j equals 0, j less than n calls 1, j plus plus. Sum equals sum plus a I j times b j. Okay. And if once we get that, so this basically assigns the sum. Now we need to assign that back to x, and I'm going to use a pointer to do that. X plus I equals sum. Okay, if you like, if you think this is easier to notate, close this brackets, maybe that's better practice. Sum, and then I need to close this grand sum, and then this now x. Though I've assigned the value of x to be the sum of each row times column multiplication, I still need to assign it to the return argument. The return argument is the left-hand side. So how do I do that? Well, this is what we'll do. We basically first create what is known as a create double matrix. Okay. This is a matrix for the return value, and that would have, since this is going to have m rows, so it's going to be the same size as B, right? So it's going to be m rows 2, n calls 2, and we also specify it's going to be real numbers, not complex. Index is real. Okay, and then once we create this, we assign this to left-hand side. So this is the first return argument. And the only thing left now is to assign x to PLHS, the pointer, right? So MEX get PR PRHS, also PLHS. So we've created a pointer for the return. We assign x to it, and x was computed here. So if everything works right, it'll give me x equals a times b. So here's what I can do. I can go here. I can do this multiplication. right? And it'll print the output A times B. I can do the same thing with my code, and then this X should agree with that X. Let's see if that works out. Okay, so here it is, 0.2307, 0.932, 0.93. So it all works out. We can try another try, and then you see that it still works out. So this is how you can multiply. Now, you might want to do some checks. If you do something nasty, like for example, let's say that I accidentally typed 4,1. Okay. Now this is a problem, right? I think this will crash the program. Let's see what happens. So this will crash this first, but just going to comment this because MATLAB will tell me it's wrong. But let me just run this. My guess is it will quit MATLAB. MATLAB will crash. Oh, it did work. Somehow it didn't work, but I think it just took the first three arguments. So sometimes when you do things which are odd, or assign memory and it's not supposed to be that way, then MATLAB will abruptly shut. It'll say crashed, and then you will have to go back and debug. So this is one of the biggest disadvantage of using C, which is it'll just crash and it'll give you a segmentation fault, and then you'll have to go and debug what the problem is. When it comes to MATLAB, it immediately tells you it's an error here, and you can easily fix that. So this worked fine, but what I recommend doing here is to make additional checks. So for example, some of the checks we can do here is the following. So once we get the number of, let me close, just move it here. So once we know the number of rows columns for A, right? And we know the rows for 2, we know that for A and B multiplication to make sense, the number of columns of A should be equal to the rows of B. And so we can check that. So here's what we do. If n calls 1, that is the number of columns of 1, is not equal to number of rows for B, right? Then we need to tell it to give an error. So the way you put an error is MEX error MSG txt, and then you can say number of rows of A should, the number of columns of A should be equal to rows of B. Right? And so now let's run this and see what happens. So now let's just change this, make this 4 and run this. See, it gives an error. Number of columns of A should be equal to rows of B. So here's how you can actually ensure that you don't get spurious inputs, and just be careful about what you check. And you can do multiple checks. There are so many things to check here, right? So we need to see that A is a square matrix, for example. You can check that. That seems to be the most important one. And then B should be a column matrix. You can also check the number of columns of B is 1, and so on. So you can do these checks and throw out errors. Something more complex than this. What I have here is a simulation, and I did this offline, of an n-link pendulum. Okay, when I say n-link, it's literally n-link. You can change whatever, you can put whatever number of links you want. So I'm going to run this file, n-link main. Okay, let's put 2. So we want to have a 2 degree of freedom pendulum. And I actually have coded in such a way that you can use either kinematics model, zero reference or homogeneous, whatever you want. Both the simulation, both those methods give the same answer. We'll try the one without MEX. So if you set the flag MEX equals 1, then it will use the MEX version. If not, it will use the regular C version. So before I do this, let me go here and take this RHS, which is, by the way, the right-hand side, and delete it because it's basically going to be generated on the fly. So I have deleted that file, and I think I can also delete animate. Okay, so there's the only file here is main and then the derive and link. So what happens here is once I set the degree of freedom, derive and link, and I'll open derive and link, it basically generates the right number of variables. In this case, it's going to be 2 for Q, U, and so on. And then it will actually write the right-hand side file. It will write the animate file because it's 2 links. So let's run this file first. Okay, I need to switch my screens. It's showing the animation on the screen. Hold on. Stop sharing. Okay, this is better. Okay, so let's run this again. So now I'm going to set NDF to 2. It will basically use the 0 reference model. It'll do the animation. Okay, and you can note the simulation time, right? Let me just make an Excel file. This is going to be a kind of fun experiment. So here is the time. So 2 degrees of freedom, and it took 0.294. Okay, or let me put 3 seconds. So this is basically giving the integration time. The way I get integration time is I set tick, and then there is a talk. Yeah, the talk, it gives me the time. Okay, so let's run this. Well, 2 is not a big deal. Let's make it 5, okay, and then run this. So there's a 5-link pendulum. Okay, and so you can see that the time it took to integrate for 10 seconds, I think, total time is 10 seconds, about 2.34. Let's just take that. I'm going to put it in my Excel sheet. So let's do 5 because this is too simple. So 2.34, 5 links. And maybe I should move this down. So DOS, Matlab, okay. And then I'll do the version with C. Next files. And then I'll do the C version. Okay, so that's fine. 2.34 is not bad. Let's do 6. That was double the time. It was 5.8 seconds. Okay, so let's take that and then save it in the table. And then that's 6. Let's do 7. And I think I'll just go up to 8. I won't go more than 8. And you can do the 9 and 10 and so on later. So you can see that actually is, there's a position vector of simplification which is doing it. That's taking a little bit of time when it reaches around 7. But that's not the part of the TikTok. TikTok only takes the time it takes to integrate the equations. So once the equations are derived and the equations are written in the right-hand side file in Matlab, how much time it takes. So that's 12 seconds. I'll take that. I will put in a file. Okay, and then I should remind you that what's happening here is it's actually generating this file every time I do this. So you can look at this file to see how the equations look like. This is for 7 links. Okay, that's the equations. The file is not too bad. It's 391 KB. Okay, let's do it for 8 and I'll stop at 8. So if you go over 8, you go to 9 and 10, then what I would recommend is you want to remove this simplify. This simplify causes a lot of bottlenecks. So just remove it completely from this, and it'll be much faster. So it wrote the files, and now we are doing tick-tock to find how much time it takes. Okay, so that's the 8 link. And it took about 29 seconds, which is almost half a minute. Okay, so let's put this down. Okay, now let us now think if we start doing a more complex system, like 8 link is not very complex really. When we have humanoids, we're talking about 20, 30 degrees of freedom. You are looking at a very lengthy equations, which will take forever to integrate. Like 30 seconds is a lot of time for eight links. So let's look at the right-hand side file. And we see that we do the usual thing. We take the mass, so by the way, don't open this file in Matlab. It will just cause a lot of problems when you're trying to scan through it. It's going to slow down Matlab. Don't do that. I just try open it in text editor. Okay, so there's a mass, there's Q's, which are okay. Now this is the mass M1, 1. That's 1, 2. So there'll be 8, 8, right? So that takes a lot of things, a lot of time and space. And then I think somewhere, so there's G, and of course there's a G I compute, there's a C I compute, and there's a mass I compute. And this A is M inverse G and C, which is not a big deal because mass now is going to be, well, it's a numeric value, right? It's going to be 8, 8, and then G is 8, 1, C is 8, 1. So once you have this M matrix, G matrix, and C matrix, this computation is fairly simple to do. The issue is that putting all the symbolic variables in this fashion in these matrices M, G, and C. So this is the part which is the most time consuming in terms of MATLAB to do the computations, because again, it's a scripting language, goes line by line. So it would be nice if we take this part of the code and put it in MATLAB so that MATLAB takes care of this. So it will basically find the M matrix, find the G vector, C vector, pass it back to MATLAB, and MATLAB will do the M inverse this. But the main symbolic part is taken care by C. So this can be done if you go here and say, let's see, I started at 5, I think. 5. So let's put 5. And then all you need to do is say flag MEX equals 1. Okay. So what will happen in that case is that it'll actually derive the MEX file. So you don't see any MEX. Let me just delete this. I keep the gateway file. So this is my gateway file, which I will, which is probably, which is the one which I don't delete because that's the file which I wrote down by hand. What will happen is that it will create the right-hand side file. It will create this file, get dynamics file, which basically creates the mass matrix CG given the state and given the parameters. So it generates this. There'll be a file called get dynamics .c, and it'll also generate this RHS file. So here we have nlink RHS, which will generate the nlink RHS MEX file, which is needed to run with this file. So let's run this for a 5-link pendulum with flag MEX set to 1. Okay, so this is the 5-link, the same pendulum, but now this is generated and simulated using C file. Okay, so you can see the time is 0.605. See, we already saw a big saving. It's about, 3 times, 4 times. Okay, so let's look at what was generated. So what I did was, just like there's a RHS MEX file, and I can open this in MATLAB totally fine, because what it does is basically it does it gets all these variables out, but then it calls this gateway file, and it basically is, that's where the heavy computation goes on, finds M, C, and G, right? So once I do that, it calls this file, and the file which has all that computation of the symbolic stuff is actually dynamic mex.c. No, sorry, not this one. It is the geteom.c, so equations of motion. So if you open that, you will see that that file is pretty big, just like the RHS was, but now it's outsourced everything to C. Okay, so we got that. Now let's run this for more cases and see how the time savings are. So 6. That's 0.83 seconds. Okay, let's put it there. Try 7. Okay, that's the 7-link simulation. It took about 0.86 seconds here also. Okay, so that's 0.86. Okay, and then finally 8-link, which took the most time in the Matlab version, about 29 seconds. Yeah, the 8-link simulation. Okay, so that took 1 second. So let me just put it down. 1 point. Okay, so there is the comparison. If you keep increasing the degrees of freedom, Matlab just the computation time almost it doesn't quite get squared, but it sort of maybe a little bit more than being it's nonlinear. It grows. Maybe it's not exponentially fast, but it still pretty much takes a lot of time to compute. To go from 5 to 8, it almost becomes 15 times more, right? From 2 to 29, and then 0.6. But when you look at seats, the time remains almost constant. It's 0.6 for 5-link. It's 1 second for 8 links. So this is the advantage of mixing your heavy computational parts to C. Now, if you are doing real-time control, and if you're using a Matlab to control the system, then you might also want to do mixing of the computation part, because then it takes a while for Matlab to actually produce an output. 1 second is fast, but I would say it's not really fast when it comes to real-time control. So even though this is great for certain systems, 1 second might be a little slow in case of real-time control. But most of our computations here are really offline. We're doing these offline computations to find a controller, which we'll then implement on hardware. So I wouldn't be too much worried about 1 second for simulation time on a desktop. Okay, so